All right. Good evening, everybody. My names are Akigbe Israel, and I will be taking the this unit model, which is mechanical measurement and fittings in waste management. Thank you very much for joining in. Please, when you join, do endeavor to put off or mute your mic. Thank you very much. Now, what's the introduction for this course? Now, a brief r- guide into what we'll be doing in this whole journey. So, we're going to be talking about measurement. We'll talk about standards. We'll talk about errors. We'll talk about limit and fit, workshop practices, and fittings. All of this with respect to what happens in a waste recycling plant or a waste management facility. So, one of the objectives is that we'll demonstrate proficiency in the concept of measurement. Now, what is measurement? Why do we take measurement? Where is measurement being applied? How to take measurements, measuring tools, etc. Also, we would comprehend the standards of measurement in place. Now, we'll talk about measuring tools also, such as micrometer, the vernier tool, direct and indirect measuring tool. So, this course, in this roadmap session, this course is a module that is scheduled for a duration of 1 week, which is categorized into the virtual session and the physical. What we're already doing right now is the virtual session, and this virtual will consist of measurement concept, the measuring standards, errors, then measurement exercises. While the latter portion of this module will be the physical session, which entails the practical hands-on and workshop practices. I also want to point out that for any of us to be qualified to go into the workshop practices, you must have successfully completed this module of the virtual class, which means you understand the concept of measurement and fitting, and as a result, you are qualified to then come around for the practical hands-on in the workshop. I'll also iterate here that you will be requiring safety gears such as your PPEs, gloves, safety gloves, safety boot or hardcover shoes, your coverall. Now, overview of mechanical measurement and fitting. So, let's paint a bit of concept. Now, measurement is a system of communication and as well on the basis of an agreed standard, promoting consistency across various engineering practices. And you have workshop practice. Now, let's give a bit of background. Now, whether we like it or not, all of us can agree to the fact that at some point in life or in our daily activity and routine, we have actually carried out measurements one way or the other, but not paying attention to the fact that what we just did successfully was a measurement process. How do I mean? Let's take a very simple analogy. When we were very much younger, I, for one, I remember my parents would, take broom and measure the size of my feet just so they can use as a reference to know my shoe size. Now, that alone is a form of measurement. However, we have a limitation of having no standard. That broomstick will not match or may not match most likely for someone else because it is not an agreed standard. So that way we have done some bit of measurement. So now let's now establish what measurement is in other areas. So measurement is used widely in various industries, recycling and waste industrial plants inclusive. In recycling plant and waste management facilities, you may have standard systems like degrees Celsius for temperature, meter cube or centimeter cube for volume of waste, pressure as Pascal, etc. All of these parameters and quantities being measured in a recycling machinery to measure varying quantities. Now, however, in a more mechanically fundamental aspect, we'll be working with measurement standard for dimensioning a piece or a component being worked on fundamentally. One of the things we also look at is interpreting dimension that may serve as guide while working and carrying out mechanical related exercises in waste management and recycling facilities. So when we intend to carry out certain operations where we need to make something exact to this, trueness to form, etc. Measurement can serve as a form of guide. So they tell you, okay, how many mass of waste are we churning out from this particular conveyor that is transmitting waste before it is being built? What is the volume in centimeter cube or kilogram? What is the weight? So these are form of standards in measuring. in industrial floors for waste management. Now, why measurement? We want to ask. So now, back in the ancient time, one of the challenges associated with measurement was the lack of standard, meaning a high level of what inconsistency in measuring, as there weren't any agreed standard of measurement. Well, there was, but not as commonly agreed. Just like we have in today's world, that you can see measurement agreed the same standard everywhere across the world. Now, take for instance, which I already gave a small analogy before. Now, another analogy is that take for instance, when we're very much younger, for those who love football, one person might decide to use his feet as a means of measurement to get the distance of the goalpost. He has to do on goalpost A and goalpost B. Someone else will not want to do that because there's not so much of a certainty that it's going to be the same distance because of what varying feet sizes. Similarly, in measurement at the time, in ancient time, there was not really a certain standard of agreement to maintain consistency in standard for measurement. Now, measurements, therefore, similarly in waste management, can be used to quantify variables as volume of waste, temperature of the waste, mass of the waste, etc. It can also be used for decision making. Remember why I say it can serve as a guide when you're interpreting. Now, for instance, take for instance a gear that is being enabled, that is enabling a shredding operation. So we have a source of rotary motion that is then connected to a gear to increase the ability of a shredder to be able to shred waste materials. So now take for instance, we want to replace that gear that does the shredding operation that is connected such that it helps to aid shredding operation. We need to know certain quantities, like we need to know the diameters, the thickness, the depth of the bore, or the length of a waste carrying conveyor for plant layout purposes. So take for instance, we want to incorporate a new portion of or a set of machinery, in this case a conveyor that carries what waste. So we need to know the length before we start making any plan that will be transferred on the industrial floor for decision making. Now, also for communication and trade. Now, you would also agree with me that during the or in the course of our lives, at some point, we have gone to markets where we need to buy certain things, and what you hear is, okay, how many yards do you want to get? How many inches, how many feet do you want to get? It is a means of communication and trade. So you want to go get something, you want to replace a part. Take for instance the same gear, you want to order something from a manufacturer. You give your specifications, which will come in what in certain parameters, of which measurements can be a parameter and other things. Importantly, in communication and trade, measurement is also being applied. So now this is just a brief exercise. We can do that and drop, send to me via mail, or we can have an engagement session on the WhatsApp with this. Now, where is measurement applied? He just give me 5 areas or examples of where measurements can be used or being used. Trust them that we are following. Okay, thank you very much. Now, what is measurement? In this session, we'll also talk about inspection. We'll talk about the standard used in measurement, which, of course, they are metric system, imperial, or English system. Then we proceed to the errors, types of errors, safety. Okay, so I haven't given us a bit of background where measurements can be used, why measurements, the challenge that come with measurements. So now, what definition best suit or best describes measurements? Apologies. All right, sorry. Apologies for that. Okay, we are back. So, like I said, after giving the background, we've given the background, I've established the background concept of why measurement is needed, how that in everyday life and activities we actually do a form of measurement or the other. I mean, sometimes you are trying to set or align something, you use your eyes to gauge it. Oh, shift a little bit more to the left, move it a little bit more to the right. Those are measurements one way or the other, but there just wasn't any standard attached to it. Now let's talk about measurement. Let's give a definition that best suits all of these things we have considered, then say this is measurement. Now, measurements, to measure, we must have the intended object of which we aim to know its dimension and respect to a what calibrated standard. So measurement, therefore, we would say is the comparison of a piece, comparing a piece, a component or an object that is undergoing test or mechanical operation with a known, I'll further buttress, agreed standard. So that way there's consistency established between me, you, other workers, other engineers, such that whatever is being measured here, whatever is being used here as a measuring tool, I will get the same value if I'm in America. I'll get the same value if I'm in New York. I'll get the same value if I'm in Canada, so that there's an agreed standard across board. Now, what's inspection? Inspection is also checking, confirming dimension result of a piece, or not only for a piece, you can also, inspection can also be applied in the regard of accuracy of how reliable a measuring equipment is. So inspect that, oh, this measuring instrument that I'm using that is calibrated with a standard is still reliable for me to carry out what's dimensioning or measurement. So then, what are standards used in measurement? Like I said earlier, and now also we are in special application and special industry. We may have other form of measurement, other standards that may exist, but fundamentally, on a general scale in engineering practices, any form of works that has to do with measurement or not, with measurement, you find two systems in place: the metric system, the imperial or English system. And we'll also still proceed to talk about the types of error. Now, standards that are being used in measurement. There are two major standards of measurement in general use. Now, like I earlier stated, there may also exist other standard form of measurement in special areas of application and purpose, but fundamentally, we do have two: imperial standard or imperial system, and the metric standard or metric system. So now, the imperial system. Now, this system is also known as the English system. However, it is gradually superseded by the metric system due to the fact that it entails fractional values when computing the total arithmetic value. As a result, it makes communication sort of challenging and interpretation of dimension a little bit challenging. Now, it can be read, no doubt. It is still, some people, like I explained, it is in place, but however, it's superseded by the metric system. So you still have some people or some engineers that, by experience, they've worked with a lot of imperial machines. They've done a lot of work with machineries that requires or that was calibrated or was built around the imperial system. And so you will still get your value, there's no doubt. However, there's the lack of ease in communicating. Now, take for instance, I tell you to measure the length and breadth and the height of an equipment or a piece or something. Now, if you're to use imperial system, you have things like a foot, 2 feet. Now, at some point, when you begin to have values that is somewhat greater than 1 foot, but not necessarily getting to 2 feet. You may have something like 1 foot 1/4, 1 foot 3/4. You might have something like 1 foot 8/16. Now, take for instance that the length is 1 foot 3/4 and the breadth is 2 feet 3/4. So if I tell you to sum up the total value of what the length and breadth is giving me in perimeter, there's the challenge of computing the arithmetic value. So first off, you have to consider the whole feet value, then 3/4 plus 1/4, that's 3/4 plus 1/4. Then you start having to do fractional LCM, do those conversion and do those calculation before you sum up. So that time, that ease of communicating is actually not so flexible with the imperial system. I've ever since the advent of the metric system, because metric is just so straightforward and easy to communicate with. Now, in imperial system, they are expressed, or the unit of the imperial system is expressed in inches, in feet, and in yards. So you say that 1 foot, that's not supposed to be 1 feet, supposed to be 1 foot. 1 foot is equals to 12 inches. Now, let me also iterate here that if you look around your environment, take for instance those container trucks that are used for shipping, etc., you would notice certain things like figures having apostrophe and quotation mark. So when you see any figure that has apostrophe, that figure is actually represented in imperial, meaning it is in feet. So take for instance, I see 9 apostrophe three quotation mark. The apostrophe there signifies or indicates that that value is in feet, while the quotation mark is in inches. So if I see 3 apostrophe 12 quotation, that's 3 feet 12 inches. All right. So now we've established that 1 foot in inches by its standard that is agreed upon is equals to 12 inches. So would we right to say that 3 feet is equal to 36 inches? Does anybody have any opposition to that? If not, I would go over to explain how we arrive at that. All right. So now, to further buttress the imperial system, I provided a link in the Google Classroom already. If you go to the other measuring equipment and resource, where I actually dropped some links for you for a careful study. Now, I would encourage that we visit those links. In just about 4 pictures or images, certain things have been depicted to consolidate what is being said here. I know as adults we can have busy schedules, so that's why I'm breaking it down as easy as possible. Then a link, should you forget certain things or something, you can always reference that. All right, let's proceed. Now, the metric system. The metric system is a widely used system, much easier to work with and to compute total arithmetic value in dimension for an object or a piece. Now, it is also expressed in an increasing or decreasing order of tens. As a result, you have the prefixes in milli, kilo, centi, hecto, etc. Now, from conventional secondary school days, where you hear that, remember those units of 10 millimeter makes 1 centimeter, 10 centimeter makes 1 decimeter, 10 decimeter equals 1 meter, etc. Now, the metric system, like I said, is very easy to compute and work with. So it's just a matter of, if you want to represent your values in a higher unit of metric system, you either multiply it by 10 or you divide it by 10. Now, take for instance, we already know that 1,000 meter is equals to 1,000 1,000 years meter is equals to 1 kilometer. That's 10 raised to power 3. So if I want to represent my value equivalently in kilometers, I multiply 10 raised to power of 3. I don't know if you understand what I just said. Good. So we can also agree that in this case here, that 1 decimeter equals to what? 100 mm. That's 10 raised to power 2. Now, so similarly, these ideas, this measurement system makes it easier that way for us to communicate, to easily move to a higher unit in the metric system or go to a lower unit in a metric system. So the ease of communication is so easy. Let's give that same example of measuring our length, the height, and the breadth. So take for instance, I tell you to measure a length, and the length is 15.7 mm. I tell you to measure the height, and the height is 12.5. It is very straightforward to make the arithmetic computation and give me the total value, as opposed to imperial system. So this is one of the unique difference between imperial and the metric system. The ease of communication. Like I will also still say, please take your time, in your spare time, do visit the link and the resources that I have placed on the Google Classroom. All right, so we proceed from here. So now, having established these two fundamental system of measurement in place, let's talk about errors. So what are errors? Now, in the course of measuring, yes, there's chances for error, or there are chances for error. It's bound to happen. It is prone to happen. So what are the types of error? What can we do also to try and prevent error, etc? Now, errors are bound to happen, and as a result, they can be catastrophic in result and altogether allow for misinterpretation of values. Now, to mention a few, you have errors which can easily be eliminated, easily eliminated errors, which can result from arithmetic error or alignment error. So arithmetic error has to do with, now when you're making your computations, you make a mistake in adding up or in totaling the value, or making your subtraction, etc. Then upon reviewing your values, you can point out your mistake and correct it. So this kind of error is easily eliminated. Alignment error. Now, alignment error usually stem from the fact that you're taking your measurement at an angle of what you're measuring, or what is being measured. I repeat, Alignment error will occur most often when you're taking your measurement at an angle off from what is being measured. So it is always advised to avoid alignment error that you're in perpendicular position, that's right in front of what you're measuring, or at angle 90 degree of what you're measuring. So that way the chances of parallax, which is a result of alignment error, is avoided. Now the second one is not easy to eliminate errors. Now take for instance, I give you a piece of diagram to interpret. Now it is assumed whatever the value is there, it is assumed by, it's a standard practice everywhere in the world, that that value, take for instance, there's you have the same length, height, and breadth. They are given in values 15, 30, and 45 respectively. If no unit of measurement is specified, it is agreed as a standard worldwide that or those values, those figures, are expressed in millimeters, not centimeters, not metric, no, sorry, rather, not meters and not kilometers, rather in millimeters, except if stated otherwise in the diagram, because sometimes you might interpret a diagram which the result, when established, is a big piece, and of course that diagram cannot, as big as it is, cannot fit into a paper. So they have to reduce and scale it down such that when you're interpreting it, you apply the scale and you have your desired result. So now that scale itself, if whoever that designs that drawing makes a mistake in that scale, because you work with the scale and have no idea that there's been a mistake in that scale, that error is so difficult to eliminate. As a matter of fact, you can't eliminate it because you've gone ahead with it, you've proceeded with it, and now the result is catastrophic. Are we together? All right. Reading error. This can also stem from either you or the measuring instrument not being in accuracy anymore, which is, it is out of accuracy, and as a result, you used the measuring instrument, and you using that measuring instrument to read off value, you are getting what? A wrong value, because the measuring instrument is out of accuracy. All right. Now here's just a few measuring tools to take a look at. Now in this measuring equipment here, you see what we have: filler gauges, we have straight edge. Those straight edge is not represented here. We have calipers, vernier calipers, micrometer, dial indicator, etc. We'll talk about marking out or marking out tables, measuring and marking out. So now pay close attention and observe that I have two instruments here, which you have two arrows pointing to, and I indicated what indirect. So your measuring instrument or your measuring equipment can be categorized to actually two types. You have the direct measuring tool, you have the indirect measuring tool. So now what comes to mind? How do I distinguish between these two? Now, if you look closely, also you observe that almost all, or in short, all the measuring tools, aside from these two here that is indicated as indirect, all of them have a form of calibration. Let's look closely. Good. Now, how then do you identify which is direct, which is indirect? Now, usually the indirect measuring tool are not necessarily used for measurements per se. However, they are used to compare distances, compare diameters, compare length from one piece to another. So it's comparison between two or more pieces. Now, in this case, when we do the comparison, we would require a calibrated measuring tool to read off the exact value. So it would be right to say that indirect measuring tools are actually measuring tools that do not have calibration and requires the aid of a direct measuring tool to read off its values. Now, I'll go back to my simple analogy. Now, remember those times where your parents use, or like in my own case, my parents use broomstick to measure your feet just to serve as a reference, for your feet size. Now, if I want to know what exactly that feet size is, I can then take that broom, which is indirectly a form of measuring tool. I take that broom directly and I translate the value, reading it off from a calibrated tool. Take, for instance, your measuring steel rule, or popularly known as ruler. In the workshop practice is steel rule, you will see steel ruler, but not plastic, but instead it's steel, made of steel. All right, if you take a look at the vernier caliper here also, you see that it has calibration, so which means that the vernier caliper is a direct measuring tool. Direct measuring tool require no aid. You can read off the values directly from them. They have calibration. As a result, we do not need an external aid to translate our values. If you also look at the filler gauge, it is embossed each unit of what's called values on those blades. If you look at your dial indicator also, that looks like a sort of pressure gauge. He has calibration and he has some form of numberings. And also on your micrometer, I believe this is clearly understood. Okay, we then proceed. Now, let's talk about vernier calipers. Now, a vernier caliper is used in reading linear dimensions. Now, you notice that this linear dimension is in capital letter to emphasize that it is primarily or solely, let's first of all establish that primarily or solely to do linear dimension. However, vernier calipers can incorporate other features that allow us to do further or to carry out further measuring variable as measuring height, depth, diameter, etc. Now, if you look closely at this image here, we have a portion where it says depth rod. Now, if we want to measure depth, we use this depth rod. Some vernier caliper provide accommodation for this, while some don't. They just read solely, internal diameter, external diameters, and linear dimension, basically. In this case here, from this image here, we can see the depth rod, which allows us to also do a further measuring ability of taking out dimension regarding depth. Now, you see these internal jaws here, these external jaws here. These internal jaws allow us to measure internal measurements. Take, for instance, the internal diameter of a ball. What I mean when you hear the word ball, it means a hole. So take, for instance, your bearing housing that has a hole to mate with a shaft. You can measure the internal diameter using your vernier caliper, these internal jaws. Also, the external jaws. Now, point two, it is solely or primarily used for linear dimension. Now, on vernier calipers, most of the times, the accuracy of the tool will be embossed by the manufacturer. Usually, from experience, will be between 0.02 to 0.05 mm. So it will be stated there. Usually, the ones I have seen personally are 0.02 to 0.05. But like I said, more often it's 0.02 to 0.005 you actually will find. Now, how do we read a vernier caliper? So please pay attention here because I really want to point out certain information here. So I need you to get this concept as much as possible. I know we can be busy, but just follow me here while I take you on this journey to understanding how to read vernier caliper. Please just a minute. Apologies. Okay. All right. Now, I said there are three concerns when reading a vernier caliper, which are now what are the things we look out for when reading a vernier caliper? The main scale. And I also pointed here that we have to first identify the main scale and reading it either in inches or metric. But in our case here, we'll be reading off our values or we're translating our dimensions in metric system. We identify the main scale, the vernier scale, the point of precision. Now, I would shuffle in between those images so that you understand and we can see what this main scale is. Now, if I go back here, this image here you see here, a portion of this image of this vernier tool is a main scale. It is fixed. While that portion is what is actually movable relative to the fixed one. Now, for easy remembering, because I know we're adults, might have too many things we're doing. So, if you should you forget that, which is the fixed, which is the movable, how does it play? Now, take for instance the human skull. In the human skull, we have a portion of which is movable and a portion which is fixed. Now, from the upper portion of the mouth, where that incorporates the face to the eyes of the human skull is fixed. Now, that fixed part will be called or will be analogous to saying it's our main scale. While the movable portion, which is the jaw, our lower jaw, the jaw of the skull entirely, is the movable portion. It moves relative what to the fixed portion. So the fixed portion of our vernier caliper is the main scale. The movable portion in the illustration of our skull will be our jaw, which is the vernier scale. Now let's look at this just to establish what I'm saying. Now this is just a simple animation to actually a makeshift to point out what the main scale and the vernier scale is. Apologies, permit my my calibrations here, but look at this. Do we see the arrow pointing indicating the main scale? We can see that one is fixed while the other one slide or move relative to the fixed one. I'll play it one more time. I believe we established that now. So now we can tell that the one that is fixed above, which is just in its own position, maintain its own position, is what is um actually the main scale. While the one that is able to move back and forth is what the vernier scale. Are we together? So let's go back. Now we've been able to identify what is the main scale. Now the next will be how far. Now remember that this vernier scale, or rather the vernier caliper measures linear dimension in the sense that how far have we traveled away from the main scale with the aid of the vernier caliper, with the aid of the vernier scale. I repeat, your main scale. How far has the vernier scale traveled in linear dimension away from the main scale? That's the first thing to consider. So to be able to do that, you have to identify the main scale. And that's why I showed you that image or the animation. So your main scale is fixed. So now when you're trying to read your linear dimension, you consider the distance by in your measurement. How far has your vernier scale traveled in linear dimension away from your main scale? Away from your main scale, your zero on your main scale. Now, I will go back to the animation so that this I will shuffle between the two of them so that by repetition it stays in memory. Now, look at one thing I observe also. Now, observe that in this main scale here, you have zero on the main scale. You also have zero beneath on the vernier scale. What would that mean? If I move my linear dimension or I travel with the vernier scale some distance away from the main scale, there will be a separation or a clear distinction of how far I have moved from the zero on the main scale to the zero on the vernier scale. Now let's look at this. Now we can agree that we have moved some reasonable distance comparing the zero on the main scale and comparing the zero on the vernier scale. So that's the first thing to note. So then we then translate our value in mm. So now let's look at this. Apologies, I'm sorry. Now look at this in real life, the real physical vernier caliper. We can all agree that this portion here below this calibration here that is beneath, on which we can see 0.02, where we see yes. Now that is the vernier scale which is moving. We can see that we've moved some distance away from the zero on the main scale. As a result, we cannot even see 11, we cannot see 10, we cannot see 9 all the way to 0 because we've moved some reasonable distance away from the main scale. The starting point of the main scale, we've moved a reasonable distance away from the starting point of the main scale, and this is how far we have traveled in linear dimension, which the zero here is pointing to. The zero here is actually pointing to, a lot of us said 12, which that's expressed in centimeter. Like I said before, your answers are to be expressed in millimeter except stated otherwise. Now, yes, slightly we are almost close to the answer that it is 12, which if we multiply by 10, that's converting. Remember I said if you're converting from a higher unit of metric system to the smallest unit, you multiply by 10. So let me also reiterate that millimeter is the smallest unit in the metric system of measurement. So we are all to make our conversions to the smallest unit unless stated otherwise. So in this case, where we say 12, centimeter is greater than millimeter. So to convert to millimeter, we have to multiply by 10. And as a result, we have what? As we have all said, 12, it is 120. But now this is not exactly on 120. If we pay close attention. Now, in between 12 to 13, we have calibrations. When I mean calibration, I mean those single individual lines. Those single individual lines are actually 1 mm representing, which means they're incrementing by 1 mm. What do we have? This is 120. The next one is 121, 122, 123, 124, 125. Now 125 is the slightly longer calibration line in between the 120 and 130. Then 126, 127, 128, 129, 130. In the case of if we're to do this in centimeter, it would be 12.1, 12.2, 12.3, 12.4, all the way to 12.9. Then we have what? 13 centimeter. I believe this makes sense. We're in sync. Okay. Now, if we pay attention, having said that each calibration represents a single um, incrementing with a single let's look closely now. The zero, where is it pointing? We can see it's in between two calibrations. As a matter of fact, it's even tending more to the second calibration. Good. So we have this as 121 point something. Now, how do we get that extra point value? That remainder, that small point something. How do we get that remainder value? Now, that is where our Vayner scale come into picture. That our Vayner scale helps us understand or helps us read off that small extra value. Now, let's go back to the concerns. Now, the second thing to look at, remember, we're seeing under reading Vayner caliper and the concerns to look out for when reading the Vayner caliper. Now, the Vayner scale, which is the movable component on the Vayner scale, it moves relative to the main scale as to how far. Can we see that in distance, either or depth or height of the components to be measured, how far we have traveled? The Vayner scale. Now, on that same Vayner scale, we then look for a point of concision. This usually on this Vayner scale, the accuracy is usually embossed, like I said, by the manufacturer. Now, the point of concision is translated on the vernier matching with the main scale. How do I mean here? I mean, so now, when you have moved your successful distance, first by identifying your main scale and how far you have traveled, from the zero on your main scale away on your vernier scale. Then on that same vernier scale, we look for a line, or rather a calibration that makes a perfect straight line with the main scale. That perfect straight line will be our point of concision. Now that value, we'll read it off on the vernier scale and add up. Now let me show you, let me take you back. Now look at this. Now we've established that this is 121 point something. Now let's look out for on the vernier scale. Where do we have, or where is there a similarity of our vernier scale? Where do we have any calibration on the vernier scale making a perfect straight line, aligning as making a perfect straight line on the main scale? Now let's look closely. Now if we look at number 6, or the figure 6 that is on the vernier scale, look at figure 6. Just as we are approaching the calibrations that are close to in between 6 and 7, just as we are about approaching 7, we see that there's a perfect straight line, right? Good. Even figure 7 has a perfect straight line, right? So now here is the rule. You pick the first perfect straight line that has that perfect concision is the first one you pick, and you record its value. So now, if you pay close attention, if you pay very close attention to this vernier scale, it is embossed on it. We can see that it's written 0.02. So which means that each calibration so when I say calibration, just to make it easier to understand, each line you are seeing that is represented here, it is what 0.02. So take for instance, you have 0 here, 0.02, 0.04, 0.06, 0.08, then you have what 1 or 0.1. Excuse me. So in between each calibrations makes up 0.02, incrementing 0.02 So now we've already understood, or we can tell what is our our main scale value, which is 121 point something. That remainder value is what our vernier scale helps us to get, and which by trying to get that, we have to look at where we have a perfect concision. That's where the calibration, any calibration line at all on the vernier scale makes a perfect straight line, aligns as a perfect straight line on the main scale. All right. Now we are saying we're taking the value, the first line that is just before figure 7, or value 7 on the vernier scale. So that will be 6.002, 6.004, 6.006, 6.08 rather. Now if this is 6.08, we add it to 121. Since we don't know what the exact value is, 121 we're seeing here. So 121 plus 6.08, what we eventually have is 121.608 eventually, so approximately 121.6. And if we observe closely in our main scale, if we observe closely the 121, you see that the calibration of the 0 on the vernier scale is very close, or almost close to the second one. It's not exactly at the middle. So which means 12.6 approximately 122. We can see we are close. So now this is what vernier caliper helps us to get. That level of accuracy, those small values. Now in areas where we need those precise, we're working with extreme amount of precision. Vernier caliper is one of the precision tools you can use to get those extra small values in the case of allowances, limit and fit. Hmm? All right. So having said that, let's look at this. Now, of course, we can guess what this is, right? We can have a guess of how far this main scale, or rather the vernal scale, has traveled in linear dimension with respect to the main scale. Now let's look at this closely. Can anybody guess, at least guess what this is? I know we have smart people here, so we can actually guess this, or we can actually figure this out. Good, 8 mm. So this is 8 mm. Yes, 8 mm. Now, when we do not have any perfect coincision line at all, in this case, we're almost not having any coinciding line. So what will happen, or what our value will be interpreted will be that this is exactly 8 mm, meaning 8.00 mm. There are no remainders. So your piece or whatever you must have measured is exactly 8 mm. That's in the case where there is no point of coincision, which means exactly this is what you have. Now, just to iterate that, we can have some level of consistency. Now, take for instance, because your point of position, the first one you may see, now look at this previous image, we actually have two lines that is coinciding perfectly. So you may choose to choose 7. I may choose, or probably because of where I'm reading, in the condition I'm reading my vernier caliper, I happen to see the second one, which is 7. That is the second coinciding line, and I use 7 as my own point of position. Another person may use 6, or rather the calibration before 7. Here's one thing to note: your main scale reading is to be consistent. When I mean consistent, if I give you, I give the other person, I give Miss Chioma, I take another colleague, and I give everybody vernier caliper to read this. Your main scale value reading will be similar, should be consistent. However, your remainder value, that's the point something, may not be consistent because your point of position, where you read your point of position, may just be different. I don't know if you understand. It may just be different. It may be different from you, may be different from the other person. As a result, that remainder value may be different, but close to in similarity. So, but if your main scale reading is now very far apart, I mean, then there's a problem. You've one way or the other made some arithmetic error. Are we together? All right. So please do confirm that you can hear me. Indicate your challenges in the message section, or you can drop it on the WhatsApp. All right. So I believe this is clearly understood. Now, this is exactly what 8 mm. There's no point of concision. Then our value is exactly read as 8 mm. If it was supposed to be in centimeter, to be expressed as what 0.8. Remember that I said if you are moving a higher unit in the metric system, you divide. If you are coming from a higher unit to a lower unit, you multiply. So let's keep that at the back of our mind so we can always remember we multiply. Are we together? All right. All right. Now, just as similar as, like I said, to every vernier tool you find, they have similarities. Once you understand the principle of how one vernier tool works, you can almost read any vernier tool that exists at all. Now, look at this numbering here. Number 1 is actually a vernier height gauge. Number 2, okay. So apologies, this number 2, the numbering don't match. So actually, this number 2 here is a vernier protractor. Used to measure angles and degrees. Now, number 3 here is a vernier depth gauge. You can also see that one of these image here is a digital one. So literally, all these measuring tools have their digital version. However, in a case where, in an event where the digital reliability of our measuring tool goes bad, we are then resolved to using or reading it this way, as we're able to understand the concept. If not, we'll be stranded. Now, this vernier tool we are seeing here, this vernier height gauge, is not necessarily a measuring tool. And I'll explain why. Now, if you look at this base here, look at this clearly. We have some portion where there's calibration, this vertical beam. Now, to this base here, this base does not have what calibration, and that height, because now that base has taken some reasonable amount of height, that height is not accounted for. So, as a result, if we use it to measure the base, because of the base is not accounted for, we may have or we will be short of some length of some Now look at this vertical beam is actually your main scale, which is fixed to this base. Now look at this portion where there's a label diagram that says the vernier scale. Of course, we already established that the vernier scale is what moves, is it moves relative to the main scale. So which means our vernier scale, once we see a measuring to that, one is movable, the other one is fixed. It kind of incorporates what a venial tool principle. Similarly also to the vernier protractor, one is fixed, the other is what a main scale, or rather the other is a vernier scale, which is actually the movable one. Then also for your depth gauge. Now, if you look closely also, this base here actually is made flat. Now, flatness is one key thing in measurements so that we can have a good reference point. Flatness is very important, so please take note. All right, now let's talk about micrometer. I believe we do not have any questions so far. All boxes have been ticked, and I see we are together. Thank you very much for your participation and engagement. It's wonderful. So let's proceed to micrometer. Now, another yet useful measuring instrument which has a higher accuracy of 0.01 mm is the micrometer. All micrometer, just like the vernier, all micrometer tool uses the same principle. Now, once understood, this same principle applies across other micrometer tools that are available. Now, it is majorly used to measure cylindrical in nature components or pieces. It comes in different ranges, 0 to 25, 25 to 50, excuse me, 50 to 75, 75 mm to 100 mm, etc. Now, this image you're seeing here, this particular micrometer you're seeing here, is actually 0 to 25 mm micrometer. Now, just this arc, this thing that makes this arc here, this piece that makes arc, is where you will see the indication of which range your micrometer is. So, like I already pointed here, that you may have 25 to 50, 0 to 25, 50 to 75 mm, etc. Which will mean that, so in an instance, take for instance, if this was supposed to be a 25 to 50 mm, which means the smallest value that micrometer will be able to read will be 25 mm, and the maximum it can read will be 50 mm. So they come in sizes, which we have available here. So now let's look at this diagram with all level of keen eyes and observation. So I'll be shuffling between this diagram and the further explanation so that we can understand certain concepts. Now look at this here. You see this is your anvil and your spindle. Is the measuring what faces. Now this face must be flat. They must be flat. I repeat, it must be flat so that we can actually have a perfect sitting face or a sitting surface for our measurement of our measuring tool to hold our piece properly. Are we together? All right. Now also look at that. We have something called a spindle there. Now that spindle, if you look at it, it's a single rod that is connected to this micrometer screw we can see. Now look closely. You see that the micrometer screw, the threads on the screw, it looks like a bolt. The distance, the threads on the bolt, they look very fine, which is it's actually a very fine screw. So now once we rotate it, by the ratchet stop rotate this spindle, what happens is that the entire piece, because the spindle is connected, everything rules as a single piece. Now, key areas for you to look out for when reading this micrometer or using the micrometer: the anvil and the spindle side. We look at the barrel, which is here. We look at the thimble and the ratchet stop. Now, it is important, or the ratchet stop there, I would emphasize, is a safety aid. Safety aid in the sense that, so when you are rotating, there's every chance that you may have gotten to the last part of the revolution and still rotating. So this ratchet stop helps to disengage that human input, that rotation, that force of rotation we're applying, so that we don't wear out this micrometer screw. Because the real principle, what is the sole thing that's making this a micrometer, is actually this micrometer screw. So if it goes damaged or it goes bad, what happens is that our values in reading will be what? Error prone. I don't know if you understand. Our values will be what? Error prone. So we do not want any issues with our micrometer screw. As a result, it's best to rotate with the ratchet. Now look at this thimble. Now the thimble is actually this portion here that has this slant, then a consistent parallel dimension. Let me show you more physical. Look at this here. This you're seeing that has this slant on both ends. Then eventually you now have an even diameter is your thimble. As of this case here, a more realistic representation, we can see that there's somewhat some slantiness. Then afterwards, you have a consistent diameter. Now that is your thimble. Also, now the key things you look out for, you look at the barrel, the thimble. Now this thimble, you can as well rotate your spindle from the thimble because all of them are one piece. And if you notice, this internal thing we are seeing here, this screw we are seeing here, is actually housed by the thimble just as a means of protection. But for us to see what's going inside, that's why we have it as this kind of cut out section. So this way, once I rotate the ratchet, because everything is all connected to the spindle, in such a way that it's connected to the spindle, the thimble rotates, the thimble rotates, and at the same time, the spindle also rotates. All right. So now, reading the micrometer. Now, when reading the micrometer, we are concerned with what? Two particular parts and a condition. Now, that part, let me reiterate. Like I said, I will shuffle in between this image and what is being written for you. Is the barrel and the thimble. The barrel and the thimble. All right. So now, the measuring surface of this. Oh, excuse me. Now, when reading a micrometer, we are concerned with two particular parts and a condition of the micrometer to sum up our total reading. But before taking measurements, confirm the following: that the measuring surface of the spindle and the anvil must be evenly flat. Remember, I already itemized or I iterated why flat surface is necessary for us because of our reference. So that that flat surface helps us to take proper measurements. If not, we may have alignment error in the course. Now, the measuring surface of the spindle and anvil must be evenly flat and no form of rust. If there's any form of rust, most likely it will cause a dent on that flat surface or contours, which would give us irregular sitting face for the piece we want to measure, and as a result, some would have been some short. So that's some millimeters short. Now, the spindle also confirm that the spindle rotates easily and freely. Why? So, if it's a micrometer that has been in frequent use, if it does not rotate freely, most likely the micrometer screw that is inside, which is the chief principal component of the micrometer, is worn out. Now, upon bringing both faces together, that's rotating it with the ratchet stop, bring both faces together. Don't add excess or undue pressure. Just bring both faces together. That's by rotating so such that the anvil and the spindle face are touching. Let me go back. This is the anvil and the spindle face. They are touching each other, but not with undue force. Just slightly. When you bring them together, there should be no ray of light that passes through. Now, when all of this is confirmed, you can actually now read, use this to read your values. So, like I said, we consider reading on what? The barrel and the thimble. And I've showed us here where the barrel is and where the thimble. Just for further clarity, this is the barrel that has a consistent parallel dimension, or rather a parallel diameter. Then the thimble is one that has a bit of slant on both sides and a consistent diameter. Then this here is your barrel. And you have a locking ring also. So now the barrel and the thimble. The barrel of any micrometer tool has axial in bracket horizontal line pointing to the thimble. Now, this line is used as a reference to get the value of reading on the thimble. Now, in this practice here, there's something called a terminology called datum, or a reference point, or a reference line. So datum, basically datum, is actually, it can be a point, it can be a line, or even a surface with which all your measurements can be taken from. Take, for instance, your origin zero when you are working with your graph in our conventional mathematics works. If you're going to start making any curve, any radiant curve, any graph at all, you know you must have your origin zero from which will be our starting point. So if you should you forget what a datum is, use that illustration to remember that, oh, a datum is can be a point, a line, or a surface from which we start our measurements from which measurements are started from. Hmm? I hope that illustration helps us to remember what a datum is. All right. So now the barrel is in two divisions, or in let me say two categories of whole mm and what half mm. Now let's go back. Sorry, I mean forward. Now look at this. This is the barrel here. Now, I say we have a division or a portion of the barrel where it is in whole mm. Whole mm means what? Each line of calibration is incremented by 1 mm. And we also have a portion on the barrel where each calibration, each line is incremented by 0.5. Now, look at this. If this is 0, the next one is 1. 1 plus 1, the next one is actually 2. 1 plus 2, the next one is 3. 1 plus 3, the next one is 4. Now, that is what the whole mm, because it's incrementing in what? Incrementing values of 1 mm each. Now, the one beneath is incrementing in the values of what? 0.5. So, if this top portion is 0, the top plus this one below, if this is 0. If this is 5, what? 0.5. Then, if this is 0.5, 0.5 plus 1 up above is 1.5. Is rather 1. Sorry, excuse me. If this is 0, this beneath is 0.5. What we have here is 1. What you have here beneath is 1.5. You have 2, 2.5, 3, 3.5, 4, then 4.5, etc. Now, we made mention that on the barrel, we have an axial line or an horizontal line. Now, this horizontal line is what you see here that goes all the way pointing to what? To your reference. Is a reference pointing to your thimble. Let me take you back so we understand what I just said. That we have what? In any micrometer tool at all, we have an axial line pointing to the thimble. So that axial line is the reference that points to the thimble, and this line is used as a reference to get the value of the reading on the thimble. Now, the upper and the lower portion of the barrel represents what? Whole mm and what? The 0.5 mm division, which is what I've already explained. That you have a category, a portion, or a division where they are incrementing, the calibrations are incrementing by 1 mm, and the one beneath is incrementing by what? 0.5 mm. Now, remember I said that the chief principal part or component of or what makes the micrometer tool is actually the micrometer screw, which is a fine thread. It is a single piece that is connected to the spindle, connected to the ratchet, which if you rotate it, the entire piece, because it's like a one piece, will rotate. So from the word spindle, when you hear spindle, spindle actually means anything that rotates. So if you hear anything they say like a machine spindle, it means that portion of piece or that component, that portion actually does rotate. So now, because per revolution, remember I made mention of rotating, it has a micrometer screw. Because per revolution of the spindle, the micrometer will travel half distance. So if I rotate once, I have successfully moved what? 0.5 in distance, which is half 1/2. If I rotate 2 times, which will be what? Good. 1 in distance. And the thimble is calibrated into 50 equal parts. Let me repeat that. If I rotate half or once I move half rotation or revolution, excuse me, once I take one revolution, I go one revolution, that is what? Half already. I have successfully moved a distance of half I have gone by half from my initial position. So if I rotate 2 times or take 2 revolutions, I have gone 1 successively. So because we also would make reference to how far we have gone in terms of the distance, there is an axial line provided on the barrel so that while we rotate, remember that I said that this rotate as a single piece, the spindle, the micrometer rotate as a single piece, and on the thimble also rotates. So because the thimble rotates, we also want to know the equivalent of the rotation. So the thimble is, calibrated into 50 equal parts. So if I rotate once, that is half millimeter multiplied by 50. I don't know if you understand this. If I rotate once, if I just make the rotation as one revolution, it will mean that I have moved half multiplied by how many number of calibration do I have on the thimble, which is equals to 50 equal parts. So this is what I mean here. Look at this. Let's look at this image. Now we see that this is 45. If we count 46, 47, 48, 49, 50, which is actually represented as 0 also. Are we together into 50 equal parts? So we can see this axial line here, this black horizontal line here is pointing towards 46. So how do we represent? Because this axial line is our reference when we rotate. So we want to compare how far we've moved. This line, compare it how far we've moved. Let's get that value on the thimble, how far we have gone. So that calibrated line that we have gone on the thimble, what is the equivalent? Hmm? What is the equivalent? So we now have the thing of half mm. We've moved half mm multiplied by that calibration that our axial line points to. We multiply it by, oh sorry, I take that again. Now that calibration with which we have got we've gotten to on the thimble, the calibration with which we've gotten to on this thimble, it will be 1 out of 50. I want to get that because everything is equal to 50. So each calibration will be 1 out of 50, 1 out of 50, one calibration out of the 50 calibration that exists. And remember, for this to rotate, or for us to get any reading on our thimble, which means must have rotated or must have moved some revolutions. So that is actually half. So how many number of revolutions have we gone? So if we go 5 revolutions, it will be half. That's 5, like more like saying 5 times half times 50. But instead, to make it easier to understand, it will be when I go 1 revolution, it will be half of 50. So that will be 1 over 2 times 1 over 50, which will then give us 0.01 So which means that every value, every single, what this translates to be is that every single value you get on your thimble when you make the rotation, in this case now, this one here is pointing to 46. If 46 is the answer here, we multiply it by what? 0.01, because we've gone 46 or the 46th calibration of 0.01 or of the 50 equal what revolutions, which we must have multiplied by half. So that will be, our value. So whatever we get on the thimble, we'll multiply by 0.01. So now let's look at this. Let's look at this. Now we already know that this is 0. Incrementing here is 1, 2, 3, 4. Beneath here is the 0.5. So now does that condition come into play? We can also see that here there's a plus a 0.5 Morse code that is showing. So now the condition is if your half on your barrel is visible, you add it up. So first, what we want to get, we get the total reading in our barrel. First, what is the total figure? What is the total value in a barrel? We'll get that out first. So this is 4 first. There's a 0.5 that is visible. We add the 0.5 to it. If the 0.5 is not visible, your thimble will directly resting on your number 4, which means is 4 So now, but now that this 5.5 is visible in the 0.5 division, we add 4 plus 0.5. So the total figure of what is reading or what's being read on this barrel is what? 4.5. We note that, pen that down on one point. Then we'll now transfer. This is our reference line, this axial line, this horizontal line. Where is it pointing to on the thimble? It's pointing to 5. Then you multiply that 5 by the accuracy of your micrometer, which is 0.01. That'll be 0.05. So we now add the total of your barrel, that's the total figure of your barrel, and what is being translated on your thimble. You sum them up together, then you get your final answer. So having said this, we will agree, or the summary of reading the micrometer will be that micrometer, we're able to generate this formula that it is barrel, your whole and half division. Now that is if the half which is the 0.5 if it is visible, you add it together. If it's not visible, you just take your upper division alone, your whole division, you take that alone, plus whatever is being read on the thimble, multiply by what? The accuracy, which is 0.01. So even if should you happen to forget on sentence, if you can remember this coined formula, I just coined, I mean that's how it works, but I just coined it, I'll just bring it out so that it's easier for you to work with. The total figures in your barrel plus thimble multiplied by the accuracy is equal to your final answer. Now in this case here, when we are reading, we see that this is 4 plus the 0.5, 4.5. Then it is the axial line is pointing to what? To line 5, to calibration 5, multiplied by 0.01. The total here on this left, or this is my right, on the right hand side here is 4 points. mm. I don't know if you understand what I just portrayed. All right, so now let's look at. I believe we understand this now. All right, good. So now let's look at this. So this here is this upper portion is the whole mm. The one beneath is the what? 0.5 mm. 0, 1, 2, 3, 3 mm. Beneath here 0, 0.5, 1, 1.5, 2, 2.5, etc. like that. So let's solve this together. What do we have here? Well, not exactly 4.5. Look again. So okay, 3.5. Yes, 3.5 because the point 0.5 is visible. If you look closely, the point 0.5 underneath the axial line is visible. So we have 0, we have 1, 2, 3. Then there's a point 0.5 line here that is showing that is visible. Are we together? Hmm? Good. So now this in this case here, where you have this rather the axial line here is pointing to what? 46. So we multiply 46 by our you know our accuracy 0.01 and sum up what we have with what? 3.5. The total of everything will be what? 3.96 mm. Are we together? You punch that in your calculator. So 3.5 plus 46 in brackets in parentheses 46 times 0.01. Add it up together. You should get your final answer expressed in mm. All right, so this is wonderful. I like so far the progress and the participation with everybody. Thank you so much for your time. All right. Now, should there be any further question, I also want to encourage everybody, please, like I said, resources are made available for you for your convenience and careful study at your convenience time. Like I said, these materials are just very short, brief. I mean, they're like one page, but about like 4 images just to represent things that have been said here. So in case you forget, express in simple English so that you can always refer back to them. Mm? All right. So uh, just a minute. Just a minute. Okay. So I believe, do we have any question now? I believe it's all fine and good here. We would continue this session tomorrow, and please let's do endeavor that we come online much earlier so that we can reduce some amount of time. There's quite a lot to cover, but also do encourage others that for some reason could not be able to join to try and join for tomorrow's session. Any question? Right. Thank you very much.